JLF Brave New World welcomes you back to our second session of the day. Those of you who missed out on our earlier session, the Shadow King, Maza Mingiste in conversation with Nandini Nair, and all our other wonderful sessions featuring Piku Iyer, Erling Kage, Ruskin Bond, Elizabeth Gilbert, Alif Shafak, Gloria Steinem, Margaret Atwood, Oran Pamuk. You can catch them on our Facebook page, JLF Litfest, and on our YouTube channel, Jaipur Litfest JLF. It's been an amazing 8 weeks with over 600,000 views and a reach of over 2 million. Our official radio partner is Red FM, Bachate Raho. Our next session is The Dance of Life, Roger Highfield and Magdalena Zernicka-Goetz in conversation. A compelling discussion on how a few tiny cells becomes the fantastically complex whole that is a fully formed human body. Roger Highfield, Science Director of the Science Museum Group, and Magdalena Zernicka-Goetz, Caltech and University of Cambridge developmental biologist, takes us through a moving celebration of the balletic beauty of life's beginning as they discuss their co-authored and critically acclaimed The Dance of Life, Symmetry, Cells, and How We Become.
Thank you.
Museum Group. He has completed his 8th book, including the, and he writes for Wired, and he's a visiting professor at UCL and the University of Oxford. Magdalena Zernicka-Goetz is a professor at the University of Cambridge, where she runs a laboratory and leads a team of 17 postdoctoral scientists and graduate students. Her work on embryos won the People's Vote for Scientific Breakthrough of the Year in Science magazine. Please do remember to comment and ask questions by typing it in the comment section. In case any of you drop off due to bandwidth issues, you can find us on our YouTube channel, Jaipur Litfest JLF. And in case we drop off, just hang in there and we promise to be right back on Facebook. Ladies and gentlemen, The Dance of Life, Roger Highfield and Magdalena Zernicka-Goetz in conversation.
Thank you so much, Sanjoy. It's wonderful to be back with the JLF. Thank you to Namita and William as well. And of course, it's great to be reunited with Magda, who's actually on the other side of the planet in Caltech. And it's interesting for me that it's 15 years to the month when I first talked to Magda for a Daily Telegraph article. It was at the suggestion of Sir John Gurdon, who went on to win the Nobel Prize. I didn't realize at the time he was a very important character in Magda's development as a leading developmental biologist. And he said, she's doing amazing work, you've got to write about her. Then over the years, I noticed again and again headlines to do with her research, whether it's synthetic embryos, challenging the 14-day limit of embryo research, or the remarkable story of her son. So we got together to write The Dance of Life, and we're sort of telling the story of life and looking at life from 4 different angles. There are kind of 4 intertwined stories there. We've got the amazing story, as Sanjoy said, of how one fertilized cell turns into 40 trillion cells in the human body. We've got the story of how very basic research can shed light on how the human body develops on problems like infertility and so on. We've got the story of Magda's life and her research in this field, and in particular what happened when she was pregnant at the age of 42 and confronted with an abnormal test result. And then the final strand is really about what it's like to do research in science when you're a woman. So I think I'm going to try and gallop through those 4 Dance of Life themes. Magda, I've talked how you've dedicated your life. You've really dedicated decades to studying the dawn of human development, those first couple of weeks of development. What's been your most surprising discovery?
Well, first of all, I want to say it's really incredibly nice event that I am able to be here, and I'm so delighted and that I am able to talk about our book. And indeed, the first question that you are posing is an excellent one, because the first discovery that I've made was very controversial, and this, I imagine, shaped many years in my in my life. And this is really this discovery that you, Roger, discovered me with. So this was really all related to the symmetry breaking event. That I should perhaps explain what it means is that we start our life with the very spherical, symmetric, beautiful egg. But when this egg cleaves into smaller and smaller cells, some of those cells have to become different than the others. And this is absolutely essential for some cells to make one part of our body, let's say head, and other cells to make the other parts. So this was extremely important to identify when and how this symmetry becomes broken. And it was always thought that our eggs, mammalian eggs, so human eggs and mouse eggs that I often study as a model for mammalian embryo, do not break that symmetry until very late in development, and maybe only around day third of their life, some cells become positioned in different places of the embryo, and this is how, through the position, they develop their identity. So I have to say that totally by chance, we discovered that it is not the case, that cells start to differ from each other much earlier, that when the embryo has only 4 cells, which is really on the second day of our life, some of those cells develop their unique characteristics. Some of those cells are more totipotent or more able than the others, so the cells are not equal to each other. Some are more equal than the others. And this was really something that we didn't expect, we didn't aim to discover. It was against the dogma of those years that was established over 50 years or more. So this was very, very challenging to communicate this news first to the scientific community. And this was not very popular. I have to say that it took 10 years to really stand by those results, as I was confident that we didn't make a mistake, and slowly convince people that this is really the case. And other scientists in the meantime joined and provided the beautiful mechanism of how cells become different from each other. So I imagine this discovery, Roger, that you you met me with, and this one that John Gurdon recommended to talk about, was perhaps the most controversial part of my life, and the toughest one.
I can understand. I mean, the way science works is skepticism and challenging each other. But obviously, there's a fine line between doing that and perhaps being over skeptical. But maybe we'll talk about that towards the end of discussion, when we talk about the sort of fourth dance of life story. But just tell me, it sounds like symmetry breaking, the fact that you've got these 4 cells in the early embryo, and in effect, that they're beginning to understand their destiny. That sounds very arcane, but that's got some very important consequences, hasn't it?
It does, because first of all, this is telling us that when we look at the human embryo, if the same is true for the human embryo, because our studies was on mouse embryos, but mouse and human embryo at these stages of our life are extremely similar to each other. Visually, they actually can't be distinguished from each other. And it shows us that when clinicians look at this very early embryo, it might well be that at this early stages, 4, 8 cell stage, they would be able to say which of those cells are more potent to make the body and which of those cells are more potent to make the structure that will connect the body with the body of the mother, placenta. So this is one practical reasons for which we really need to understand when and how it happens. And of course, it's also important in our evolutionary context of understanding the world. This brings mammalian embryos closer to embryos of all other living creatures.
But of course, you do study human embryos, and there are very special restrictions on doing that. But I suppose one of the fascinating things is that when you look at these details of the way the human embryo develops compared with, say, a mouse embryo, although there's lots of similarities, there are actually quite profound differences as well, aren't there?
You are right. And those differences start particularly at the time of implantation. So initially, the first few days of development are very similar, although when you look in the detail, now we can look at the individual genes that become active in different types of cells, we found that often they are the same genes, but they might be active at different time points, or they work slightly differently together. So that's why scientists are still trying to understand human development independently of mouse development, although the first lessons, the lessons of how we can, how life built itself, we always would use mouse embryos as a prototype for our understanding. But yes, work on human embryos is extremely important to really identify whether those same mechanisms that we identify in the mouse operate for human embryo.
And of course, one of the things you've done is to extend the time that you can grow embryos in the laboratory. And you've mentioned implantation. Just talk through some of the issues around, we are, I think by law in the UK and many other countries, we're not allowed to grow embryos beyond 14 days in the laboratory. But your research is beginning to question that. But of course, there are reasons to do it. And I wondered if you can talk us through that a little bit.
Yes. So I wish to say that our discovery that some cells are more equal than the others in the very early embryo, and that there is this early patterning, that it's not strict, but nevertheless guides cell fate decisions and which part of the embryo become, was accidental. I didn't plan to discover it. We didn't want to go there, but we discovered it by chance. But extending the time, extending the length of time that embryo can stay outside the body of the mother so we can study it, was not accidental. So I really wanted to do it for many, many years, but I was always discouraged as my mentors believed that it would be extremely difficult study to undertake, not for ethical reasons, but for practical reasons. So it took a lot of courage and persuasion.
I should say, when you say mentors, it's not any old mentors. You've got 2 Nobel Prize winners as mentors. So when they say they think it's a bit of a waste of time, that's quite serious opposition, really.
It was those 2 mentors, but also my earlier mentors that were also very influential in my life. So I was very lucky to have those mentors, and I'm very happy that they guided me through, because maybe if I tried to embark on that tree at this very early stage of my life when I was just PhD student, maybe it would really jeopardize my progression in science. So maybe I really needed to mature to be able to open that door. But why did we want to study embryo beyond, in the case of human embryo, is beyond day 7. In the case of mouse embryo, it is beyond day 4. The critical event that happens on day 4 for mouse and day 7 in humans is that embryo becomes embedded within the body of the mother. So embryo invades the body of the mother and start to depend on it. And this was extremely difficult to mimic in the laboratory settings. Yet this critical stage of life is extremely fascinating, because the whole morphology of the embryo is rebuilt, is changed, and each individual cell now start to grow for the first time. And the tissues are formed, and those tissues interact through the very mysterious dialogue to really build the future organism. So this is really magical moment of our life. Often we say, which moment of our life is the most magical at this stage of our life? I would say the implantation for sure is, because this empowers the embryo to make something bigger, indeed physically, because it grows for the first time, and something much more complex. So we wanted to study this stage of life, because whenever we were trying to understand the process, we were able to only go until certain points. So it is like if you are looking at your life and you can live only until whatever day may be 18 years of your life, and then you cannot follow on. You cannot find out what happens to your destiny or chance by which you are establishing yourself further. So this was the reason, really, to follow the cells in their journey, in the dance of life through that implantation process. And yes, so actually, Roger, I'm so sorry because I digress. Your question was slightly different. Why day 14 and whether we should move beyond that day? So this 7 days that we just opened for study a few years ago is between day 7 and day 14. And we had to stop our experiments on day 14, not necessarily for technical reasons, but for reasons that this is the boundary that we cannot cross. So the question is, should we one day initiate process of crossing this boundary? So I believe we should discuss that, because indeed this next 7 days in our life are equally exciting. This is the time when cells start to move through the line called
You've frozen Magda. I'm not sure if we can pick up the link there. I think while I'm not sure whether we can recapture Mag.
Roger, we've got you both. Don't worry. I think your internet connection may be a little unstable, but go ahead, Magdalena.
Yes. So I see myself, but I think Roger's face is not moving. So, but we hear his voice. So should we carry on?
Yes, please. Just carry on, Magdalena.
Okay. So what I wanted to say that the next, that on the day 14, the magical event that happened at the time is formation of the line called primitive streak. You can think about this line as a line on the road that indicates the direction of the car movement, so direction of the traffic. And this line is very important because this identifies the feature through which the cells will be migrating to initiate formation of the body. So we cannot now cross that line. We cannot we can look at the processes that leads to establishment of that line, but we cannot see how cells move from through this line to initiate the process of body formation. And I know that there are discussions right now whether we should allow studying that stage of development, which is on the other side of that line. So it will be beyond day 14. Right now, we are not allowed to do that, but there is a hope that maybe one day it will be possible. However, I am very cautious on that statement. I believe that it should be very thoroughly discussed, and we should take public with us and explain to everyone why it is important to understand the next few days.
Of course, another aspect of your research, which I think is fascinating and a little bit sort of disturbing in equal measure, is that rather than creating embryos by mixing eggs and sperm, you've built them by blending 3 different types of so-called stem cells, these parent cells of other kinds in the body. Just talk us through a little bit about why that's important, and again, why it's important to limit, why you think it's useful research, but equally it's got to be limited very carefully indeed.
So the need for making, I don't like this term synthetic embryos, but I remember when we were writing our book, we were discussing together between us, should we call them synthetic embryos, should we call them embryo-like structures, and be much more careful in the way we refer to them. But let's call them synthetic embryos for today.
Okay.
So why they are important?
My bad, actually. I shouldn't have used this terrible slang term, but actually I think it efficiently makes the audience understand why this is surprising in a way. But go on, carry on.
Yes, no, it's a good term. It's a good term because you are right. This really sends the message of what they can become. So why they are important? So first of all, let me just say very briefly how we are constructing them. So we know that embryos are made out of stem cells. So all of different tissues originate from the egg, and the egg has to make stem cells for different tissues first, and then those stem cells interact. So we try to see whether we can mimic this process in the laboratory by starting not with the egg, but starting with the stem cells that were generated by our colleagues in different laboratories, starting with Martin Evans, my mentor that Roger mentioned, who got a Nobel Prize for actually establishing the very first embryonic stem cell line. So we started with that line, and so far it was not possible to create embryo structure with that group of stem cells. But looking at the embryo development, mouse and human, through that implantation process, showed us the principles that we have to obey for the embryo to be normal. And then we use that principles I'm thinking now about the right number of cells, the right environment to teach stem cells how they should behave. And this was unbelievably successful. I have to admit that I couldn't believe that we would be able to recreate these very first steps of embryo life that happen at the time of implantation with just embryonic stem cells. So we did that first. And then we thought, well, if we can mimic this part of embryo development, what if we take stem cells that make placenta, or stem cells that make a yolk sac part of the embryo? This is the part in which embryo itself will grow. And of course, placenta is the part that will connect the baby with the mother. And can we recreate those interactions? So we took trophoblast stem cells and blocks together. It's maybe not as childish as this because we have to control environment. Nevertheless, the magic happens when you allow those cells to interact with each other. So our influence of how those cells should develop is minimal. We just have to provide the right environment, the right medium, the right number of cells, and then we can let them initiate their own conversation. So those structures are not identical to embryos. Right now, they are not. They're extremely similar and they're extremely informative about the processes that happen in the development at that time. And why they are so useful? Because it means that we can learn a lot about early stages of our own development, about those stages at which many pregnancies fail, many miscarriages happen without the need of using embryos. So we can complement the need of using embryos with the use of those synthetic embryo-like structures to gain the molecular understanding. When I'm saying molecular, to gain a, let's say, deeper understanding of what fails and how can we fix it.
So moving on to the second sort of strand of the dance of life, and this is applying this understanding to solve very real medical problems. And you've mentioned one. Give me some other examples of how understanding of human development and reproductive science has changed the world.
Well, the very famous example, the one that we also talk a lot in our Dance of Life, is IVF, in vitro fertilization. So this, Roger, I know this is one of your favorite topics, so we should talk about this together. And yes. I learned from you during writing this book a lot about this event. So I want to say that I should introduce you to talk about this topic. I can start by saying that, of course, we know that it have happened first in Cambridge many years ago. And now we have many children born through in vitro fertilization. This was equally controversial, whether those studies should move on to the stage that it can be practically used to help reproduction. Roger, tell us a little bit about that. We didn't plan it this way, but why not?
No, it's fine. It's fine. I mean, I was lucky enough to meet both Steptoe and Edwards, and I dealt quite a lot with Robert Edwards. And I think what amazes me is you're absolutely right. When they prepared for, what became Louise Brown, the world's first so-called test tube baby, IVF baby, it was hugely controversial. They were sort of shunned by the medical establishment a bit as going a step too far. Although I think Edwards did have quite a profound scientific understanding of what was going on at the time. And I think we should also pay tribute to the large number of infertile couples who went through experimental IVF unsuccessfully until Louise came along. And I think for me, what is truly gobsmacking is here we are today. There's something like, and this is a guesstimate, 10 million people on the planet who wouldn't exist without in vitro fertilization. And I think it was an amazing thrill for me a couple of years ago when Louise Brown came into the Science Museum and she celebrated her 40th birthday in the museum. And there was an electric moment when we had a kind of incubator jar in the exhibition, and she could point at it and say, I started my life in that jar, which was a sort of tingling sensation on the back, hairs on the back of your neck when you realize that. But I think, yes, there are controversial aspects and so on, but it's brought immense happiness to people across the planet. Although I should say, and this is very relevant to your research, Magda, it still surprises me that here we are many decades later, and it's still quite an inefficient process, isn't it? I mean, it's more often than not unsuccessful. So it's quite an ordeal if you're an infertile couple and you undergo this whole process, isn't it?
Yes, so you are absolutely right. This what have happened then that we can now use is incredible, but it's extremely inefficient still. So I think that the research that scientists are doing, some research that I do, but also my colleagues that try to understand what happens at these early stages of our life, how to distinguish between embryo that develops correctly from the embryo that does not develop correctly. They would look sometimes identical to each other. So what are the features that we can point out, identify, that would be the very good predictor of which of those two embryos we should transfer to the body of the future mother to have a successful pregnancy is still a mystery. We have those tools and we are still developing those tools to be better and better, but there is no still one single tool that I would be able to put the finger on and say that's the best one. So a lot of what we are doing, trying to understand the basic processes of development, will really aim to develop those tools. And we are currently developing those tools here at Caltech, and we were developing them and we continue to develop them in Cambridge.
I've realised, I know people will have questions, so we've only got about 5 or 6 minutes, or a few minutes to cover our other two themes from the Dance of Life. It's entirely my fault. So, but just very briefly, if you will, in terms of applications, just tell us a little bit about stem cells and their potential, and things like organoids as well. Which are two gigantic subjects, Magda, which you'll have to compress in about 2 minutes flat.
Yes, well, as you say, gigantic subjects. So what I can say is that, so we use stem cells in our laboratory, and we mentioned it a little bit to build embryo-like structures to understand how embryos develop. But also stem cells, other type of stem cells, can be used to build organ in the laboratories, not organs that are entirely like, liver and pancreas in our body, but very much mimicking the development and function of those organs. And those are extremely important to understand how liver, how pancreas function. And we can then test different drugs that are developed in the industry to find out how we can deal with the diseases that those organs can encounter in the real life. And equally the same is true for embryo-like structures that we are creating. So we can identify, for example, whether coronavirus will be the virus that will be dangerous for the embryo. If it were to go through the placenta to the body of the embryo during early stages of pregnancy, or Zika virus. So this organs and embryos in the laboratory models are of enormous power, and this is really the last years that we can do it. So this is something that was developed relatively recently, and the impact already on science is unbelievable, on medical science is unbelievable.
Well, I noticed a few days ago, Magda, that the Times in London had a power list of scientists, and you were on that power list. And you've got a sort of one of the elements of the Dance of Life is telling your own story, which is fascinating at so many levels. One thing that might surprise people to learn is that you were actually yourself raised in a laboratory. Now, tell us a little bit about that.
Wow. So first of all, I had no idea that I am named in the Times magazine on that list. It's a honor. I didn't know at all about it until today, until this morning. What I wish to say that indeed, it was by chance I was raised in the laboratory, I guess, but it happened because when my father was offered a job as a scientist in an institute in Warsaw, in the communistic country after the war, there were no enough apartments at the time in Warsaw, and he didn't have any other place to live. So since he was offered that job in the institute, the director of this institute kindly enough offered him a space in the laboratory to create the temporary apartment to be able to accommodate my mom, who was then pregnant with me. And this is how we lived there for many, many years. In fact, it was supposed to be a temporary apartment, but the proper apartment for my parents to move me to the normal settings didn't come for the next 5 years. So people with white coats and glasses and huge smiles on their faces and doing unusual things to discover mysteries of life is just my everyday at that stage of life.
Now, perhaps much more seriously, and much more difficult issue was when you found that you were pregnant at the age of 42, and then you were confronted with this abnormal pregnancy test, which confronted you with a very difficult decision to make about whether to continue with the pregnancy. That changed your life in so many ways. I know you could talk about this for hours on end, but give us a sense of that moment and what it led to.
Well, this was perhaps one of the most terrifying moments of my life when I received a phone call from the doctor when during my second pregnancy, and the news were that the genetic testing indicated the major abnormality. There was an additional chromosome number 2, which is huge chromosome, was duplicated. So I had 3 of those chromosomes instead of pair. So this was really frightening news, and indeed this was the test of the placenta rather than a baby itself, but it is used as a diagnostic test to predict the normality of your growing baby. So why did it change my life? I just realized at the time, looking through the whole literature, that I could identify that we do not have the knowledge what happened to abnormal cells when they are developing alongside normal cells within the embryo. So in my case, this result was indicative of the embryo being perhaps mosaic. That means that some cells were normal and coexisting with abnormal cells side by side. So I decided to change the path for the next years of my research and identify what happens to abnormal cells when surrounded by normal neighbors. And we created those embryos, mouse embryos, that have this situation, and we were able to label those cells that are normal with one color and about that journey is that we identify something we didn't predict, that those abnormal cells, when they start to contribute to the part of the embryo that will make the fetus, that will make the future baby, they would be killed. They would eliminate themselves. Now the question is, and we are still studying it right now, whether normal cells help to eliminate those abnormal cells or whether those abnormal cells commit suicide. So I am paraphrasing it a little bit, but it's not far away from reality and of what we try to understand. So it was really lovely that science allows you, to a certain extent, change the pathway you are following if the problem is very important.
I suppose the important thing to say, though, is that you decided to go ahead with the pregnancy. You had an intuition that things were going to be okay. I suppose it's worth saying that nature is quite ruthless at not allowing or dealing with abnormal embryos, and so the fact that the pregnancy had developed gave you encouragement, I guess. Tell us about Simon.
Well, so Simon was born entirely normal, and he is incredible boy right now. He's really joy of my life. He is now with me at Caltech. My daughter is still in Cambridge, UK. My son is with me at Caltech, and he is really incredible boy now, not so little, start to grow, and he's nearly my height, very artistic, very, very opinionated. So we have debates every single night at the dinner time, which is, as we all know, when we have teenagers at home.
We call them rows with my teenagers, Magda. But anyway, there we are.
I think I should call them this way too.
But it's an extraordinary story. But I think people might not realize that to understand or get a bit of insight, because we'll never really know what happened with Simon. It took it took years and years and years of painstaking research, finding out ways to create chromosomally abnormal cells, then putting embryos together with a certain known number of cells and following the development. I mean, how long did it take in all? 10 years or so?
Yes, you are absolutely right. It took a long time. And actually, this part of the journey we describe very nicely, I think, in our book, when we really describe, not in too much detail, but we give a feeling of the scale of those experiments. So we have to indeed first find out the way to create abnormal cells, and then make sure that they are created correctly, so they are truly abnormal. And then we thought that we should create them in more than one way to make sure that our results are not just only about one specific abnormality, but many abnormalities. And then we had to find a way that we can film the development to find exactly the fate of those abnormal cells. And Roger, you wouldn't believe that despite that we started this research 13 years ago, we still carry on this research. So the next paper about it will be coming out next week. And we are still trying to understand exactly how those cells interact. In this case, I think they compete with each other, and normal cells are the winners. I think these are the normal cells that would win at their dance of life, and the abnormal cells will be eliminated. But how those cells compete for that success of making the baby is a huge mystery, and it's not yet resolved.
So I think let's go to the final element of the dance of life, which is actually being a woman in scientific research. You alluded to it earlier on, but you found it fairly tough, and I wondered, does this link with your decision to move some of your research to Caltech? Just talk me through that a little bit.
So you are right. I think that, first of all, I wish to say that the way we have so many incredible, remarkable, talented women in science, and we have more and more every year. I would say we have more women in science that are given a chance to become group leaders, to follow their passion, and to contribute to science equally as their male counterparts. But indeed, when you often see institutions, scientific institutions, university departments, you see that often this is the voice of the more of the men that is louder in making the decisions. And I think this is something that I aim to change. I would love to be able to be more active in changing that while I am still continuing doing science. I feel that this is incredibly important to realize how valuable way women have to contribute to science. It's often less through competition, more through collaboration, by maybe offering more unusual way of thinking, more softer way of thinking. But softer doesn't mean weaker.
Well, I think we've now, I've got some questions in from the audience, Magda. So a mixture of technical and more general. Let me start with a technical one here from Sachdev Ramakrishna, who says your work on the black box of development is phenomenal. This is the point of implantation and so on, which was sort of hidden to view for so many years. And then they say, what was the real challenge there? Was it recreating the implantation process outside the womb, or was it building a system so you could actually see the details of what was going on?
Yeah, so both. That's a very good question, because on one hand, we would like to provide embryos with all of the nutritions that it will normally encounter within the body of the mother, within the uterus, to continue this growth and to continue it normally. So we have to identify those components. So we have to find out whether we should be adding particular growth factors or particular hormones. So should it be estrogen? So that was one thing. So identify this cocktail of factors that embryo will adopt as the cocktail of factors that mother will normally provide. So this was one thing. The second one was to allow us to follow this development. And initially we have this technical dilemma that took us a long time to sort. So we were able to grow embryos or allow embryos to grow at this time, but they were growing on the platform that we couldn't film this process of development. And we want to film it because we wish to describe it first. And indeed, we had to therefore modify our platform to allow us this process of imaging.
I should bring out one element of the book that we haven't really discussed so far, sort of the artistic element that you've spent a lot of your life developing ways to image individual cells in the embryo. And in fact, on the UK edition, you can see some of the beautiful images that result to track all the details of development. And I guess that's a really important overall component of your research, isn't it, Magda?
I agree. So the research that we are doing is just enchanting me every single day with its beauty. It's just unbelievable because the embryos per se are absolutely beautiful. And this is such a privilege to find out how they are finding their own way to develop into more and more complex structures. And they do it in an incredibly powerful and remarkably complex and yet simple way. And we can also color different parts of the embryo with fluorescent dyes. And if you follow development of those dyes, of those vital dyes, you will be able to follow development of the embryo, but you also follow the development of the art. This is like art being made in front of you. So those embryos are often extremely beautiful. And you see one of them behind me. This is not particularly fluorescent image, but this is our last discovery that we are very happy because it's not only powerful in terms of embryos allowing itself to grow by making those holes that you see behind me, but also it looks cool.
Now we've got a couple more questions, Magda. Here's one from Aruna, it's much more general. How do you think the coronavirus affects an embryo? Obviously very topical with COVID-19.
So there is not yet any published information about it, but we started this research recently to look at the positioning of the receptors that would allow a coronavirus to penetrate from the mother to the baby. And I can reveal that secret, although we haven't yet published it, is that indeed receptors that would allow the protein, the virus, to go through are present at the very early stages of our life. And they're present in this group of cells that will be making the placenta. So they will be connecting the body of the embryo with the body of the mother for the nutrition exchange. So there is more research that have to be done, but that's what our current data suggest.
Another technical question here, rather good one. At the 4-cell stage, what is it that tells the cells that, you know, what's the signal, the differentiation of the 4 cells into different cell types?
Wow, this is still a mystery. So we know which genes are active in those cells that become different from the rest. So those cells that become different are actually those cells that initiate the journey on the differentiation process towards placenta slightly prematurely. So the other cells will be more totipotent, so more able to do anything. And some group of cells decide to depart and initiate the process of pattern formation. But what makes those cells unique? It's still a question. So we know which genes these cells will start to have active and which inactive, but what makes those cells unique? That's a good question. Is it coming from the egg, or is it coming from the site at which sperm enter the egg? It's still something that we would need to discover.
There's lots of questions coming in now. We've only got 5 more minutes. So I'll try and rattle through them. So Rachita Akhilesh Chauhan asks, are we overruling natural selection with the use of embryo-like structures? So there's a bit of unease there about whether this is unnatural and is going to lead to no good, Magda.
Well, with every single research like that, at the moment, the embryo-like structures that we are generating, of course, they are not good enough. They're not as perfect as the real embryos. We are trying to use them as models to understand development. The same is true when we make organoids to understand the brain function. They're not perfect brains that we have in culture in the lab, but there are parts of those brains that can function to help us to understand why it is that some of us will develop Alzheimer or another condition. Mm-hmm. So the same, we can think about embryos. They are really models to understand and improve our life. Of course, all of this research have to be regulated and is regulated. And it's extremely important that it will stay like that.
There's a fascinating question here from Rachita Akhilesh, who says, have you equated the behavior of cells with the patterns that mimic the evolution of society? So do you think in a way that what's happening in the way that societies evolve between people is happening in these vast societies of cells that we call a human being?
That's a fascinating question. Fascinating question. It's true that you can think about the groups of cells and their interactions. And I alluded a little bit to that as you think about society. So some cells collaborate with each other and send positive signals to form structures together. We never think about it this way, but I can do it. And some cells compete with each other for a space, for making different parts of the future organism. So there is a lot of interactions between the cells, how they talk to each other. Part of this talking is chemical, part of this talking is mechanical, but the secret of that language is not yet figured out. And this is one of the fascinating questions that we are trying to unravel.
In fact, I did an earlier book where we were talking about how human beings are actually the most cooperative species on the planet. And you can look at the human body as an extraordinary example of cellular cooperation. And you can also interpret things like cancer as a cell defecting from the body and refusing to cooperate and then evolving independently. So there are some overlaps there. I think before Sanjoy wraps up, Magda, what I'd love to ask you is, there are so many huge questions about human development. It's still amazing what we don't know. Just give us a few headlines about the next big questions in developmental biology and the dance of life.
Well, so you are right. There are so many questions. There is the progress in science, in the type of science that we do that works on embryos, that relates to embryos and stem cells, is incredible. But the more we know, the more questions we are posing because of the discoveries that we are making. So one of the questions that fascinates me right now we discuss is how cells collaborate with each other, cooperate versus compete. So what's the mechanism? And when they realize that they have to do it, because obviously cells don't have the little brains, so it has to work through different mechanisms. So the secret language of communication is fascinating. The other question that I am totally passionate about is the question of time, how embryo measure time. You know, why it is that pregnancy have to take 9 months, not 8, not 7, not 2. You know, can we change this time? How embryo at this early stages of its life, when it have only few cells, know how the clock works? Of course they don't, but they have to have a mechanism that certain things happen at particular time of life for the life to progress. So it has to implant on day 7. So it has to reach a lot of milestones by day 7. How embryo know that it has to do it and how this time is measured? So that's another example of fascinating question. And
in fact, it's worth saying, Magda, isn't it, is that the embryo self-organizes as well, which is an extraordinary thing, that it's it's like a house building itself or something. There's something quite mysterious there. And everything has to happen in the right order at the right time, doesn't it?
Absolutely, absolutely right. Exactly that. So how the self-organization works, we often self-organize ourselves, but not always perfectly. But embryo does, and does have to do it perfectly to survive.
And I think there must also be some more artistic elements to your. Have you managed to find new ways to visualize the dance of life and the embryo and so on?
Yes, so this is one of the things that really excites me about Caltech. So there is a lot of new technology. So Caltech is Californian Institute of Technology in Pasadena, in LA, and indeed there is a huge hope that I brought here to develop new ways of imaging embryos, to go into more detail in visualization of not only what cells do, but also what happens within the cells when they are doing different things. So I wish to understand the dance that happen within dancing cells, inside those dancing cells, because there is another type of dance there, and I'm 100% sure there is, but it's very difficult to uncover it at the time when cells are dancing, because everything is moving. And this is really what I hope to develop at Caltech as a new way of looking into the cells and new way of thinking about them.
Well, I think we're out of time now, and I don't know whether Sanjoy is going to come back to join us, or if we've lost Sanjoy.
Back. I'm back. That was just so fascinating. We were trying to get 9 months into 45 minutes. How is this even possible? It's the most fascinating conversation, and thank you so much. I mean, we really need the 9 months to be able to take it through each of the stages that both of you talked about. And for those of you who want to actually get hold of the book, and both Magdalena and Roger prefer the British version of The Dance of Life, which has got a beautiful cover, you can order it online on Amazon once your lockdown is over, and really read this incredible.
It's great lockdown reading. Great lockdown reading. Sanjoy.
Great lockdown reading, and I think a must for anybody who, IVF or otherwise. It's just fascinating how we are who we are and how each of us are different. I think that, and the fact that on the fourth cell you becomes unique, and this whole clockwork thing. Thank you so much, both of you. That was just, beyond fascinating. And I'm sorry we couldn't take everybody's questions, and maybe we can forward those to Roger and Magdalena to be able to answer and send it back to you. Thank you all for being such an incredible audience. And we thank our radio partners, Red FM Bajate Raho. And please do remember to log in on Saturday, the 6th of June, as we present the JLF London at British Library, which is the curtain raiser special weekend that we have. And we have special sessions, Salam Bombay to a Suitable Boy, Meera Nair in conversation about her work. And we have the Silk Road, Peter Frankopan in conversation with William Dalrymple. And this will begin at 7:30 p.m. IST, 3 p.m. British Summer Time, and 10 a.m. Eastern Daylight Time on this coming Saturday. And now from the Jaipur Music Stage Archives, we present Trayam. Trayam is made up of 3 accomplished musicians who've performed widely and have been the recipients of numerous awards. B.C. Manjunath on the Mridangam is a world-renowned figure and performs in multiple styles such as Indian classical, world music, modern jazz, contemporary classical, and many others. Praveen D. Rao is a versatile classical musician who's also been a music director, composer, stage director, and arranger for 30 years. And Varajashri Venugopal, singer and flautist in the Carnatic tradition, is popular for her rare ability to scat jazz compositions using Indian sargam system, which she calls Carnatic scat singing. Here's an extract. Enjoy and see you on Saturday and Sunday.
Dina dagina dina da dina da tinta da tirkirtak da tirkirtak dina dagina dina da tirkirtak dina da tirkirtak dina da tirkirtak da tirkirtak dina da dina dina dagina dina da dina dina da dina da dina dagina dina da tirkirtak dina da dina dagina dina da tirkirtak dina da dina da takita tikita takita da dina da dina da takita tikita takita da dina da dina da takita tikita takita 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 da da takita da takita tikita takita tun 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 narana tirkirtak da 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 tirkirtak da 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 tirkirtak da 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 da